Hi students, now I am going to give lecture on 5th unit in Strength of Materials 2. The 5th unit is advanced topics. Okay, so in advanced topics, the first topic is we are going to see is unsymmetrical bending. Okay, so unsymmetrical bending in symmetrical section and unsymmetrical section. So before going to start, first we have to know what is unsymmetrical bending. Okay, so while using the well-known bending equation m by I is equal to sigma by y equal to E by R, it is assumed that the neutral axis of the cross section of the beam is perpendicular to the plane of loading. Okay, so for example, this is the cross section of a beam. Okay, and this is the neutral axis, and this one is the loading portion. Okay, so they mentioned that neutral axis of the cross section of the beam, so neutral axis of the cross section of the beam is perpendicular to the plane of loading. Okay, so perpendicular to the plane of loading, so neutral axis is perpendicular to the plane of loading. Okay, this condition implies that the plane of loading or plane of bending is coincident with or parallel to a plane containing a principal centroidal axis of inertia. Okay, so what they are mentioning is the plane of bending is parallel to the plane containing a principal centroidal axis of inertia of the cross sectional beam. If, however, the plane of loading or that of bending does not lie in a plane that contains principal centroidal axis of cross section, then the bending is called unsymmetrical bending. Okay, so so what they are saying is the plane of bending is parallel to the plane where it has principal centroidal axis. Then that type of bending is symmetrical bending. If the plane of bending is not parallel to a plane where there is a principal centroidal axis, then that type of bending is called unsymmetrical bending. Okay, so you got it. So what is meant by unsymmetrical bending? So there are two reasons for unsymmetrical bending. First one, the section is symmetrical but the load line is inclined to both the principal axis. So this is the first reason, the section is symmetrical but the load line is inclined to both the principal axis. Okay, so for example, rectangular section, circular section, I section and all symmetrical section, but the load line is inclined. Second reason, the section itself is unsymmetrical and the load line is also along any centroidal axis. Okay, so this is the second reason. Okay, so example, angle section, channel section and all unsymmetrical section, and the load line is along any centroidal axis. So these are the two reasons for unsymmetrical bending. Okay, so after unsymmetrical bending, so what are the terms we are comes under the unsymmetrical bending? So first one is product of inertia. So product of inertia we'll calculate by using a parallel axis theorem for product of inertia, and then we'll use principal axis and principal moment of inertia and all. So we know what is parallel axis theorem, principal axis and principal moment of inertia and all. Okay, so I'll tell the formula. So one formula comes IUU is equal to IYY plus IXX by 2 minus IYY minus IX by 2 into cos theta minus IXY sin 2 theta. Similarly, IVV, in the book they mentioned as IXX dash or IUU, both are same. Similarly, here the IYY dash as mentioned, but IVV also we called as IYY plus IXX divided by 2 plus IYY minus IXS by 2 into cos 2 theta plus IXY sin 2 theta. Okay, so on the angle tan 2 theta is equal to 2IXY divided by IYY minus IXX. This is also one formula. Okay, so one more equation, IUU plus IVV is equal to IXX plus IYY. Okay, so it shows that the sum of moments of inertia about any two perpendicular axes remains constant. Okay, the sum of moments of inertia about any two perpendicular axes. So IUU plus IVV is equal to IXX plus IYY. So both are constant value. IUU plus IVV is equal to, we get a value, for example, K. Similarly, IXX plus IYY also gives K. Okay, so that only they are saying that the sum of moments of inertia about any two perpendicular axes remains constant. Okay, so we know parallel axis theorem, principal axis and principal moment of inertia. So after that, in unsymmetrical bending, first we will calculate stresses. Okay, so stresses due to unsymmetrical bending, the next heading is. Okay, so this is a rough figure, an imaginary figure. Okay, in this figure it is neutral axis NA and the axis EXX, the axis UU, the axis YY, and this was the axis VV. Okay, the stress calculating formula is sigma B is equal to, okay, stress acting at point B, sigma B is equal to m dash u divided by IVV plus m double dash V divided by IUU. So this is the formula for calculating stress. Okay, where m dash is nothing but m sin theta u. Okay, so component of m dash is nothing but m sin theta. Similarly, m double dash, the component of m double dash is equal to m cos theta. Okay. So these are some important points. Okay, first point, the maximum stress will occur at a point which is at the greatest distance from the neutral axis. So maximum stress will occur at the greatest distance from the neutral axis. Okay, so that point, greatest distance only, at greatest distance from the neutral axis, the maximum stress will occur. Okay, so this is one important point. Second point, all the points of the section of one side of the neutral axis will carry stresses of the same nature. Okay, and on the other side of its axis of opposite nature. So what they are saying is, suppose this is the neutral axis. Okay, so one side of the neutral axis, the stresses will be act of same nature. Same nature means, for example, compressive nature. Okay, so one side the compressive stresses are acting means the other side will act opposite nature. Other side means tensile stress will act. Okay, this is one more important point. So after that, the next is deflection of beams due to unsymmetrical bending. Okay, so here also an rough or imaginary figure. Okay, so it also has a neutral axis, axis UU, axis XX, axis YY, and axis VV. Okay, here the load is acting at the axis YYW. Okay, this is angle theta, so this is W cos theta and this is W sin theta, and deflection acting the axis U delta U, deflection acting in the axis V delta V. So the resultant deflection delta U and delta V gives the resultant deflection delta. Okay, so the angle between delta V and delta is beta. So the formula for calculating deflection delta is equal to KWLQ by E into square root of sin square theta divided by IVV square plus cos square theta divided by IUU square. Okay, so where K and all, where K is a constant depending upon the end conditions of the beam and position of the load along the beam. For example, a simply supported beam, a load is acting at the center means the constant is 1 by 48. We know formula for deflection, WLQ by 48 EA. Okay, so the term 1 by 48 we are taking as a constant. Okay, so L is equal to length of the beam. Okay, so E is n smallest and all. Okay, so next formula, the inclination beta of the deflection delta with line GV is given by tan beta is equal to delta U by delta V, that is equal to IUU divided by IVV into tan theta. Okay, so inclination beta is this angle. Okay, the angle between delta V and delta is the beta. Okay, so tan beta is equal to IUU divided by IVV into tan theta. Okay, so now we'll see a problem. A 80 mm by 80 mm by 10 mm angle section shown in figure is used as a simply supported beam over a span of 2.4 meter. It carries a load of 400 Newton acting along the line YG, where G is the centroid of the section. Calculate. Number 1. Stresses at points A, B and C of the midsection of the beam. Number 2. Deflection of the beam at midsection and its direction with the load line. Number 3. Position of the neutral axis take E equal to 200 giganewton per meter square. Okay, so in the problem they gave the figure also. So it is an angle section 80 mm by 80 mm by 10 mm. So it is an unsymmetrical angle section. Okay, so the width of the flange is 80 mm. Similarly, height of the uh, web also 80 mm. Thickness of the both the flange and web and all 10 mm 10 mm. Okay, it is given in the question itself. uh, uh, they are marking the axis also, so it is axis xx. Okay, so it is the point centroid point G. Okay, axis B y1. Okay, this is axis yy, and this is bx1. Okay, so origin point O. Okay, so this is point A, point B, and point C. Okay, so in these points A, B, and C and all, we have to calculate the stresses. Okay, now we are taking this as a portion 1. Okay, flange. Okay, the angle section, we are taking the flange of the angle section as the portion 1 and the web as the portion 2. Okay, so G is the centroid for the total figure. Okay, and we are also having axis UU and axis VV also. Okay, so first we have to calculate the x bar and y bar of the centroid G. Okay, so x bar is equal to we know the formula. X bar is equal to A1 into Y1 plus A2 into Y2 divided by A1 plus A2. Okay, the formula is A1 into Y1 plus A2 into Y2 divided by A1 plus A2. Okay, so portion 1 one's area is 80 mm width and 10 mm thickness, so 80 into 10 into Y1. Okay, so Y1 is okay, so A1 is 80 into 10 into we are calculating x bar. So x bar means A1 into x1. The formula will A1 into x1 plus A2 into x2 divided by A1 plus A2. Y bar means A1 into Y1 plus A2 into Y2 divided by A1 plus A2. So for portion 1, A1 is 80 into 10. Then x1 is for portion 1, x1. The x1 is the centroid. Okay, 80 divided by 2, 40 plus. Then portion 2 is this one. Okay, the web. Okay, so this portion only. Okay, so out of 80, 10 will go, so the remaining is 70 mm. So 70 into 10 is the area. 70 into 10 into x2. Okay, so x2 mean x direction centroid is 10 divided by 2, 5. Okay, divided by A1 plus A2. So A1 for portion 1, A1 is 80 into 10. For portion 2, 70 into 10. Okay, so we'll get the x bar as 23.66 mm. Okay, so we'll get both the values x bar and y bar as 23.66 mm. For x bar, the formula is A1 into x1 plus A2 into x2 divided by A1 plus A2. For y bar, the formula is A1 into y1 plus A2 into y2 divided by A1 plus A2. Okay, so after calculating the x bar and y bar, next we are calculating moment of inertia about x-x axis. Moment of inertia about x-x axis. Okay, so it is an unsymmetrical section. Okay, so we have to use parallel axis theorem formula. So Ix is equal to Ix plus Ay bar square. Okay, so that is the formula. Okay, Ix is equal to Ix plus Ay bar square is the formula for parallel axis theorem. Okay, so for two portions are there. So first we are calculating for portion 1. So portion 1, Ix is nothing but rectangular section only. So BD cube by 12. So 80. Okay, width is 80, depth is 10. So BD cube by 12, 80 into 10 cube by 12 plus Ay bar square. So so for portion 1 area is 80 into 10 into y bar. Okay, so from x-axis only we are calculating. So y bar is equal to so we know that y bar already we calculated y bar as a 23.66 mm. Similarly x bar also. Okay, 23.66 mm. Previously we calculated x bar and y bar for the coordinates of the centroid G. Okay, this is the centroid G. Okay, for this centroid, we calculated coordinates, that is x bar and y bar. Both the values are 23.6 mm. Here also y bar also 23.6 mm. Okay, now we are calculating Ixx, okay, with respect to axis xx. Okay, so here the y bar is, okay, for portion 1, y is 10 divided by 2, 5. Okay, so from xx axis, okay, so the distance is 23.6 minus 5. Okay, so 23.6 minus 5, so this distance. Okay, so this is 5. Okay, so totally 23.6 from here. Okay, 23.6 minus 5 gives the distance. Okay, the whole square, a y bar square, so the whole square, plus. Now for portion 2, so portion 2, bd cube by 12, so b is 10, d is 70. Okay, so 10 into 70 cube by 12 plus a y bar square, so a is 70 into 10 area into y bar. Okay, for the portion 2, the y bar is, okay, 10. Okay, 10 plus, from this distance only the portion 2 starts. So from this point to point A is, the distance is 70, so 70 by 2, 35, so 35 plus 10, 45. So 45 minus 23.6 the whole square. Okay, a y bar square. So portion 2 is, area is 70 into 10 into y bar. Okay, for portion 2, 10 plus 70 by 2, so the 10 plus 35, 45. So 45 minus 23.6. Okay, so centroid is at the distance of 23.6, so 45 is 8. Okay, so 45 minus 23.6 is the whole square. Okay, so after simplification this, we will getting Ixx as 8.898 into 10 power 5 mm power 4. Okay, since it is an equal angle section, 80 by 80 by 10 mm, Ixx and Iy both are same. So Ixx is equal to Iyy is equal to 8.898 into 10 power 5 mm power 4. Okay, so next steps and all, we have to calculate the coordinates of G1. We have to calculate the coordinates of G1 and G2 with respect to G. Okay, so I'll teach those things and all in next video lecture.